Hello there and welcome to a brand new lesson. This is How Beyond Numbers, where we learn maths the easy way. In this lesson, we are looking at number patterns. By the end of this lesson, you should be able to identify and describe the rule of a number pattern. Be able to classify patterns as arithmetic, geometric, or special ones, that is either square, cubes, or the Fibonacci. You should be able to predict the next terms of a pattern and justify the rule mathematically. You should be able to express a number pattern in words and begin writing it algebraically. And then finally, you should be able to solve real life problems that involves number patterns. So with this said, without much ado, let's quickly look into our lesson. So let's start by looking at what a number pattern is. When we talk of a number pattern, it's simply a sequence of numbers that are connected by a consistent mathematical rule applied repeatedly. You see, so just a sequence of numbers, and you have rule that tells you what the next number would be. A typical example of a number pattern is what we have here. So we have the number 4 followed by a 7, a 10, and then a 13. Now, if this continues, we say it's an infinite sequence. Okay, so what is the rule over here? The rule is simple. We are just adding 3 each time. So the rule simply generates the next term each time. With us knowing this is the rule, we have 13. For the next number in the pattern, we'll just add 3 to that, which will give us what? A 16. Then we add another 3, giving us a 19 in that order. Back to number patterns. There are so many number patterns, but we'll be considering 4 of these. The first being arithmetic patterns, the second being geometric patterns, the third being a square or cube, and then the last one, the Fibonacci type. So let's start by looking at what the arithmetic pattern is. It is very simple. It has a simple rule, and its rule is add or subtract a fixed number. Add or subtract a fixed number. That is all. Whenever we are adding or subtracting a fixed number to a pattern, then that type of pattern is an arithmetic pattern. So what we have here is even an example, you see. So if we are to say we have 3, 7, 11, 15, and then a 19. What is happening in this pattern? You realize that we keep adding what? 4. So this is an example of an arithmetic pattern. So with arithmetic pattern comes what we call the common difference. You see, we consider common difference under this type of pattern. So the common difference is simply the fixed amount added or subtracted between each consecutive term in an arithmetic pattern. So for this one, or for this pattern, this is its common difference, you see. So that is what we keep adding. For this particular pattern as well, its common difference is what? 3. It is not always positive. Sometimes it can be negative as well. So anytime we are considering arithmetic patterns, then the common difference has to be in our mind. I mentioned a word here, that is consecutive term. When we talk of consecutive term, then we simply mean the terms that appear one after the other. That is the one that is directly next to each other in the sequence. So in this sequence we have here, that is 10, 14, and 18. Then we can simply say that 10 and then 14 are consecutive, you see. And then 14 and 18 are also what? Consecutive. They appear next to what? The other one, or each other. So with arithmetic pattern understood, let's look at the next type of pattern we call the geometric pattern. Unlike the arithmetic pattern, the geometric has to do with what? Multiplication and then division. Multiplication and division. So anytime there's a pattern and we realize that they are multiplying or dividing to get the subsequent ones, then it's simply a geometric pattern. If we have 2, 6, then 18, then with a 54, you realize that if you are to multiply 2 by what? 3, it gives us a 6. If you have to multiply 6 also by a 3, we'll get an 18. If you have to multiply 18 also by 3, we also get a 54. This is a geometric pattern. So we are just multiplying each and every term by 3. With geometric pattern comes what we call the common ratio. So the common ratio is simply the fixed amount multiplied or divided between each consecutive term in a geometric pattern. So for this, our common ratio is 3. You get it? Then for the previous one, that is in arithmetic sequence, we call that what? The common difference. So arithmetic sequence or pattern has to do with the common difference, whilst geometric has to do with what? The common ratio. Now we look at another type of pattern that we call the square or cube patterns. You should know that it is not all patterns in the mathematical sphere that has to do with either geometric or common, or geometric or arithmetic. There are so many others, but then of these, the main two are the arithmetic and then the geometric. Some of the other special ones, we call special ones because they are based on mathematical structures such as the perfect square, perfect cubes, triangular numbers, and then even Fibonacci sequence. So for these special sequences, one is what we call the square or the cube pattern. The rule is just what? Terms that are made up of powers of natural numbers. You see, so with this, what we mean is you can have a 1, you can have a 4, you can have a 9, you can have a 16, and then 25, and it goes on and on and on. The rule is simple. That is n to the power what? 2. So for every number, just square it out, and then it forms part of the square or the cube pattern. You see, so the square pattern is simply to the power 2. You get it? Then the cube pattern will simply mean you have 1, 8, 27, and it also goes on and on and on. So for this, you are taking the natural numbers and then you are cubing them. You see, so all these are part of the special sequence. Let me quickly write that down. So that is it we have over here, special sequences. They are patterns based on mathematical structures such as perfect squares, perfect cubes, triangular numbers, and then the Fibonacci sequence. So we've considered the square and then the cube pattern. Let's look at one last one, which is the Fibonacci sequence. So unlike all we have considered so far, the Fibonacci sequence also has its own rule. You see, each term is equal to the sum of the 2 terms before it. So as an example, all we need is our first 2 terms. That is to say 1 and then 1. Then for the remaining, we are just going to add the 2 before it. So for the first and second term, which is 1 and 1, 1 plus 1 gives us what? A 2. The next term will be 2 plus 1, which is a 3. The next term will be 3 plus 2, which is a 5. The next term will be 5 plus 3, which is what? An 8. The next term will be 8 plus 5, which is also a 13. And it goes on and on and on. This is what we call the Fibonacci sequence. So we've considered some basic sequences, that is, including the arithmetic, geometric, square, cube, and then the Fibonacci. How do we find the rule for a sequence if given in a question? When it comes to finding the rule of a sequence or a pattern, I'll give you a step-by-step approach every time you are given a pattern. There are just 4 of them. So our very first step is to calculate the difference between consecutive terms. That is, you have to subtract each term from the next. This is to help you know whether or not it is an arithmetic pattern or a geometric pattern. You see, so then comes step 2. Now, if you're able to do that and then the differences are equal, then it simply means it is an arithmetic pattern. You write it down as D, that is common difference equals D. But if not, then we have to go to step 3, which is to find the ratio. You see, so it simply means if it is not an arithmetic pattern, then we want to check whether or not it is a geometric pattern. If it is geometric, then the common ratio we have, we represent it with R. So take note of the difference here. If it is an arithmetic and you finish finding your common difference, you name that as D. But if it is a geometric, you name it as what? R. The next thing is to say that if it is neither, then you check any of the special sequences you know, whether it's a perfect square, perfect cubes, triangular numbers, or the Fibonacci type. And that becomes our step 4. So with this, we can start solving some questions. But there are 2 more things I want you to know. That is a key principle, and then how we can describe patterns in words. So a key principle you have to note is that a rule must work for every pair of consecutive terms, not just the first 2. So after working out your rule, you need to what? Verify it against at least 3 consecutive pairs before you state it with confidence. So you don't just look for the rules and then end there. You see, verify it. Now, the conclusion of your question also really matters. So when it comes to describing your pattern in words, I would give you this template here, which says you'd list or you write the type of pattern, then plus the rule in words, then plus what verification. So as an example, you say this is an arithmetic pattern. Now the rule in words, each term is obtained by adding 5 to the previous term. Then you now verify. This is the pattern or the template we'll be using. So with all the tools set, let's now work some examples. So for our first question we have here, it says, identify the rule and write the next 3 terms. Now the sequence we have here is 6, 10, 14, 18, and 22. So the first thing we need to do is to find the common difference. Is it a common difference or a common ratio? So finding the difference, we have the difference between the consecutive terms. That is 10 minus 6. And 10 minus 6 gives us a 4. Then we can try for a 14 minus 10, which also gives us a 4. And then we have 18 minus 14, which also gives us a 4. That will be enough. But I could also write 22 minus what? 18, which also gives you a 4. Now, since the differences are all equal, then we can say that it implies that what? D is equal to 4. And then it is an arithmetic sequence or an arithmetic pattern. Or in other words, we can say it is an arithmetic pattern with common difference D equals positive 4. The next thing we need to do is to look for our next term. So for our next term, we have what? 22. So we have 22 plus 4. And 22 plus 4 gives us what? A 26. Then we come to what? After 26, we have 26 plus 4. And that also gives us a 30. And then we finally have what? A 30 plus 4, which would also give us a 34. The question asks us to identify the rule and write the next 3 terms. So we can end by saying, therefore, the rule is what? To add 4 each time. And then the next three terms are 26, 30, and 34. Very simple. Let's look at our next question. So the next one says, identify the rule and write the next three terms. It is just as the previous one. So the first thing we need to do is to find our difference. Then we proceed from there. So for our difference, we have 48 minus 96. You see, it's always the one in front minus the one behind. And that gives us a negative 48. Well, let's look at the next one. So we have a 24 minus a 48. That is this 24 minus this 48. And that also gives us a negative 24. With this, there's even no need to continue. The difference are not equal. Hence, let's try the ratio. So let's find the ratio. So for the ratio, it is also the same procedure. This one divided by this, then this, that is the third term divided by the second term, then the fourth term divided by the third term. That is to say, we have 48, then we divide it by our 96. That gives us a 1 over 2. You see, then if we have to try the next one, we have a 24 divided by a 48. That also gives us a 1 over 2. And obviously, 12 divided by 24 also gives us a 1 over 2. So that is to say that our term or our pattern here is a geometric pattern. And if it's a geometric pattern, then our R is equal to 1 over 2. You see? So now we need the next terms. So how do we get our next terms? We know geometric pattern deals with multiplication and then division. So with our common ratio being half, if you observe, you realize that the next term is half of the previous term. So 24 is half of 48, and then 12 is also half of 24. See? So if you are now on 12, then the next term is going to be what? 12 times 1 over 2, which gives us a 6. Then the next term after 6 is also going to be what? 6 times 1 over 2, which gives us what? A 3. Then the next term after this is also going to be what? A 3 times a 1 over 2, which would give us a 3 over 2, or a 1.5. And this is enough. So with that, let's write our conclusion. The question asks us to identify the rule and write the next three terms. So you can say, therefore, the rule is to divide by 2 each time, and then the next three terms are what? 6, 3, and then 1.5. As simple as that. Let's look at our third question. Our next question here says, what type of pattern is this? We have 1, 8, 27, 64, and then 1, 2, 5. Then we have to write the next two terms and describe the rule. So for now, the basic types of patterns we know are the arithmetic and then the geometric. So for arithmetic, we need to check the difference. So let's start by checking the difference. For the difference, we would try with what? 8 minus 1. 8 minus 1 gives us a 7. Then we have 28 minus 27 minus 8. That gives us a 19. Then we have 64 minus 27. That alone gives us what? That is 37. And it is obvious that it is not constant. Since it is not constant, then it can't be an arithmetic progression. So we now check for the ratios. So checking for the ratio, we have what? 8 divided by 1. 8 divided by 1 gives us an 8. Then you have 27 divided by 8. 27 divided by 8 is obviously not 8. It is around a 3.375. This alone should tell you not to even continue. It is also not a geometric sequence. Then you have to observe and then tell. So upon critical observation, you realize that this 1 here, it is actually a 1 times 1, you see, and it can even be a 1 times 1 times 1. So if you were thinking of just 1 times 1, that is the square. 2 squared doesn't give us 8, so we don't settle with a 1 times 1, but rather let's go with what? 1 cube. And 1 cube gives us a 1. What of 2 cube? 2 cube on the other hand gives us what? An 8. What of 3 cube? 3 cube also on the other hand gives us what? A 27. And it goes on and on and on. So you realize that the pattern we are looking at here is a perfect cube pattern. And that is to say n to the power what? 3. So for every term, it is linked to what? N to the power 3. That is the general rule for this pattern. Hence, for our next terms, that is, we have 1, 2, 3, 4, 5, 6. So for our sixth term, that is U6, it is going to be what? 6 to the power 3. And 6 to the power 3 gives us a 216. For our seventh term, we have 7 to the power 3. And 7 to the power 3 also gives us a 343. So what type of pattern is this? And then we have to write the next two terms and describe the rule. So we can say the rule is what? Therefore the rule un is what? N to the power 3. That is cube of numbers. And then the next terms are 216 and then 343. As simple as that. We have two more questions to solve. The last one being a word problem. So stay tuned till we get there. Question number 4. So our fourth question we have here, it says a pattern is 1, 3, 6, 10, and then 15. Name this sequence, find the next two terms, and describe how each term is formed. You have to name it, find the next two, and afterwards describe how each term is formed. So as usual, let's start with the arithmetic to determine whether or not it is what arithmetic. And we do that by finding the difference. So let's find the difference. So finding the difference, we have 3 minus 1, which gives us what? A 2. Then we can go for 6 minus 3. So 6 minus 3. 6 minus 3 also gives us what? A 3. Then we can also say 10 minus 6. So 10 minus 6 gives us a 4. Now it is obvious that we are not getting a constant difference, but there is a pattern we observe in this difference as well. So let's do the last one. That is 15 minus 10. That gives us a 5. Even though this is a 2, this gives us a 3, and this gives us a 4, and then we have a 5 here. It is not constant, but you see anything or any pattern, even with these differences, there is a pattern, and that is the differences are increasing by 1 each time. They are increasing by 1 each time. This is a property of triangular numbers. You see, so these are triangular numbers. And what do we mean by triangular numbers? They are such that each new term adds the next counting number. So we start with 1 and then 3. You see, or let's even start with 1. If we start with 1, the next counting number after 1 is what? 2. So let's add 2 to this. In other words, let's quickly write our counting numbers here. So we have 1, 2, 3, 4, 5, 6, 7. These are the numbers we use to count. So for triangular number, all you need is what? Your first one here, which is what? 1. After 1, let's add the next counting number, so plus 2. 1 plus 2 gives us what? A 3. Then we add the next counting number, which is what? 3. So 3 plus 3 gives us a 6. Then we add the next counting number, which is 4. 6 plus 4 gives us a 10. We add the next counting number, which is 5. 10 plus 5 gives us a 15, and it goes on and on and on. So each new term adds the next counting number. Hence, if we want the set one, that is U6, then it's going to be 1, 2, 3, 4, 5. So the sixth one, we would have to add what? 6 to it. And that is to say 15 plus what? 6. And 15 plus 6 gives us a 21. So the set term in the triangular numbers is what? 21. If you want the next term, we are going to add 7. So the seventh term is a 21 plus 7. And 21 plus 7 gives us a 28. So the rule that we want is what? Add increasing whole numbers. That is plus 2, plus 3, plus 4, plus 5 in that order. So that is the rule you see here. That is to add increasing whole numbers. And by increasing whole numbers, what I mean is you first add plus 2, then come and then add plus 3, then plus 4, plus 5 in that order. You see, it goes on and on and on. Yeah. So we are to name the sequence. What is the name of this sequence we have here? That is a triangular number sequence. What are our next two terms? The next two terms are what? The 21 and your 28. For this last question we have here, you can pause and attempt before you check our solution. It says the number of tiles used to build square pattern is, you have 1, 4, 9, and then 16. A builder wants to know how many tiles are needed for the 10th pattern and also for the 15th. Find both answers and describe the pattern rule. So with this, it is very straightforward. You need to recognize this pattern by now. And that is to say we have a 1 squared, that gives us a 1. Then we have what? A 2 squared also, that gives us a 4. And for the 9, you have a 3 squared, that gives you a 9. And then finally for the 16, we have a 4 squared, which is what? A 16. So what pattern do you see? It is perfect square pattern. A perfect square pattern. And for perfect square pattern, what does it mean? It simply means for every term, we have what? N to the power 2. That is the general rule for what? The terms. It implies that to find our 10th term, that is U10, then it is going to be a 10 squared. And 10 squared gives us what? 100. So for the 10th term, you need 100 tiles for that. For the 15th term, that is U15, then we also need a 15 squared. And 15 squared gives us a 225 what? Tiles. And that is just it. So we can say, therefore, the rule, our rule is what? UN equals N squared. And the 10th pattern uses 100 tiles, whilst the 15th pattern using was uses 225 tiles. As simple as that. So this ends our set of questions for this particular lesson. But as usual, I'll leave you with some exercises so that you try on your own. So here are questions for trial. You can pause the video and attempt this before moving on. They are just 5 questions and then they are very, very simple and then straightforward. We'll end this lesson here. It has actually been a very long lesson, that is 30 plus minute video. Let's have beyond numbers where we learn maths the easy way. I do hope this lesson was helpful. If there's any issue of concern, you can always let me know at the comment section, and when notified, I'll address that for you. If this is your first time on the channel and you do think it will be of help to you, you can choose to subscribe if you so do wish, so that anytime I release a video, you'll be notified as well. See you in our next lesson, and bye for now. Do stay safe.